Good evening and welcome to this afternoon's Inspired Squad WA Mathematics Methods Program webinar for your exam revision. This afternoon's topic, differentiation and its applications, and your presenter for that will be Mr. Stephen Julian. Stephen was briefly introduced last week. He's a teacher at Mandurah Catholic College with heaps of experience and has conducted many webinars for teacher training, but this is the first one targeting students specifically, and so we're hoping that this webinar series will be of great benefit to you as you prepare for your 3-4 unit mathematics exam. Just a reminder, people who have been logging in early, and it's been wonderful to see that. I've seen a great list of names on the participants list. By the way, you only see one participant listed, and that's yourself. That's just a confidentiality thing that you don't get to see who else is logged in, but rest assured you're not there alone. There are quite a few people logged in. Some people gave us feedback last week that they didn't see the initial slides that were indicating the phone-in numbers. So I'm going to type that into the text now. The phone-in number is 1800 708 203. I'll just pop that into the screen for you in the Q&A. So phone in. Or you should just get the audio. Sorry, you should just get the audio, so there's not a need for that. So you'll just get the audio through your computer. Sorry, the number for the event, 825 673 356. So that's hopefully all happening there. Just on the Q&A, please, during the session, click on the Q&A panel and type in your questions. There's Stephen and myself and several other teachers watching the webinar, ready to try to respond to your questions as quickly as we can. So without further ado, we'll just hand over to Stephen to take you into your session on differentiation and applications.
Okay, thank you, Brian, and good evening, everyone. Hopefully everyone's on successfully tonight. And first of all, it's good to see a number of familiar names and people that I know quite well. So welcome, and also to those people who don't know me well, also welcome. Just going to have to bear with me a little bit tonight. I think, like most people here over in the West at the moment, I've got a bit of the dreaded lurgy that's just knocking that I can't shake at the moment. So hopefully we get through this session pretty successfully. But if I sound a little bit like I've got a head cold, that's because I have. So yeah, bear with me with that, but hopefully it won't affect the presentation at all. So anyway, let's get straight into it. Tonight, as was mentioned in the package that you would have received, our main focus tonight is looking at the idea of differentiation and its applications. So we're going to be looking at things like trig functions. We're going to be looking at logs. One of my big focuses, which we'll only mainly focus on tonight, is notes page. Later in the sessions for the next 3 weeks after tonight, we'll give you a little bit of time. I'll have a few pre-prepared for you, but for tonight, I really do want to spend some time making sure that people are able to do that themselves if they'd like to. Brian's going to spend a little bit of time looking at some trig function work with you, and another big focus will be shortcuts and just making sure that people know how to navigate their way around the menu options within the calculator. So, getting straight into it, as I said, one of our big focuses for tonight is the review of the calculus menu options and just making sure that people are familiar about what's already there for them. I know, talking to some of my own students in my own methods classes, and I'm luckily teaching 2 Year 12 groups, a lot of them are trying to write notes pages for things that may already be available. So rather than actually trying to come up with a notes page that can do something already, if you've already got them there in the options, then you may as well use them under menu. So having a look at the first one, and you'll notice on the PowerPoint here, which will be available or is already available through the Google shared document site if you want to look at it after the presentation, If we go into Calculator, excuse me, if we go into Calculator and into Menu, you should find that number 4, which you should be fairly familiar with, is number 4, Calculus. Now, I'm going to look at a few of these options tonight, and just making sure that you've got your syntax right and that you know what you should be typing in when and where, and basically what kind of results that we can get from these. So, starting with the first one, number 1, which is derivatives. So if we go into that, this one, again, I would hope most people are fairly familiar with. There is a shortcut, by the way, which I'll talk about in a moment, but if we type in x, and then let's make this one a really easy one. I'll keep them all pretty general and generic for this part of the session. If we type in d dx and then x squared, press enter, and there's our derivative straight away. So no need to be fiddling around too much with those kind of things. Obviously, you can put in fairly complex ones, things like product rule, quotient rule, etc., etc. There is a shortcut. We can go shift and the minus sign, and that will also give us that option. So, again, either way, whichever suits. Obviously, my focus at the moment is for using the menu option, but you can use the shortcut. And the integral one we'll talk about next week, which is Shift Plus. I'll show you a few tricks with those. Okay, the next option, Menu, Calculus, and if we go into derivative of the point. Now, this one comes up with a little entry box that we can put some information into. The first one is to work out what the variable is going to be. So in this case, I'll treat it as x. The next value that you need to put in is the value of the point, and it's the x coordinate. So let's say we want x equals 2 as our coordinate. Now, we do have different options here. In the derivative box, you can actually go right, and you can bring up first derivative, second derivative if you want to get into concavity. You can even put in as many levels of the derivative function that you want. So again, if you have, for some strange reason, need to find the fourth or fifth derivative, you can actually use that, and I'll quickly show you that in a moment. But let's go into the first derivative. Okay. Now you'll notice that it pre-fills most of the information that you need. So again, if we just push in x squared, again keeping it pretty simple, and no major surprise there. If we differentiate x squared, we get 2x, put 2 in, you get 4. So again, you can make this as complex as easy as you want to. Just quickly showing you the menu option for the multiple derivatives. So let's again put 2 in. Let's go the nth derivative. Now you'll notice here it gives you a little box up the top, and you can actually put in, let's make it 4. Okay, and it'll automatically fill in. Now, be careful here, because if we put in a fairly small polynomial, obviously it'll just break down to 0. So if I made it something like x to the power of 8, and then press enter, and it will actually differentiate that 4 times for us, and then substitute the value of x equals 2 in. So again, if you were asked to do that, which is probably not going to happen in the exam, but you can actually make it more than just a second derivative by using that option. Okay, moving along. So our next option, menu, calculus. Now we'll leave integral until next week. Just quickly looking at the limit option. So again, if you ask any questions on limits, which do come up a fair bit, particularly in the calculator section, you've probably seen this one before. Limit of t approaches. Now I'm going to put infinity in here. There are a couple of ways we can get the infinity. Probably the easiest one is go through the pi button, and then you'll notice that the infinite sign is one of the choices. You could also go control and the catalog box button, which is just below the delete. That will also give you it, but probably takes one more button push. Now, the next thing I want to do is I want to put in something again that you may be familiar with. So we're going to put brackets, 1 plus. Now, the fraction button is control and divide. Again, hopefully people are familiar with that. 1 over t. Then just outside the first bracket, but before the second bracket, I'm going to put to the power of t. Now, if I press enter, we should get e. Now, hopefully people have seen that either through investigations or etc. That's obviously the limit form of the value of e. If we want to make that into something that's just a decimal, control, enter, and now we've got the decimal version. Or you could go through into the doc button and change the settings if you needed to. Okay, the next one. Most of these early ones you've probably seen a fair bit of before, but the next one you may have not played around with much, which is number 7. So I'm going to jump down to the function and the minimum idea. Now, if I do that, we get f-min. Now, obviously, we're looking at a function and we're looking at the minimum value. So something we could actually do here is think, oh, well, obviously, the first question is, what's the syntax? What do we actually need to enter into those brackets? Well, if you're not sure, what we can do is push the catalog button, which is just below the delete, and you should get this option come up. Now, if you haven't already got selected one, just push the number 1, and that will give you the catalog, and it will give you a whole list of different functions. Now, we want to go down to F-min, so if you push the F button, it'll take you down to factor. You may have to push the arrow button to go down a few spots. Eventually, we'll get F-min, and you'll notice that the syntax down the bottom here is we want the expression and then the variable. So I'm just going to escape out of that. So we want the expression, so let's again make it fairly easy, x squared, and then the variable, which is x. If we press enter, you should find that the minimum for the function y equals x squared, again, shouldn't be surprising for us, is x equals 0. Now, you might be saying, well, what about if I wanted to make it into, if I wanted to actually find the y value for that? Well, something we could do, and this is actually a nice little trick, if we actually defined a function, so f of x, and we're going to use the define idea, so control, and then next to the 9 button, you'll know you've got a colon, or you notice you've got a colon and an equal sign. And then let's make it x squared, again, staying fairly consistent there. So now what we should do is we should have our function defined as x squared. Now, we might want to not only know what the x value is for our minimum, we might want to know the y value. So a few ways around that. I'm going to press F for function. You'll notice it's in bold, so now we can actually treat that as a function that's defined. Then I'm going to open bracket, go up to menu. I could copy and paste down what I've already done, but let's just go back up and do F-min. Then the function, x squared, comma x, and if we press that, we should find that x squared equals 0, which just means that the function, when we put that x minimum in, is coming out to be 0 as well. Again, just confirming that the minimum for x squared, or y equals x squared, is 0, 0. You'll notice that there's a little exclamation mark there. If you actually do hover and click over the top of it, it will actually say operation might introduce false solutions. That generally is more important if we are getting into things like hyperbolas or reciprocal functions where there's possibilities that some of the solutions may not work under certain circumstances. It might be a composite function type situation, which again this course doesn't get heavily into, but it's just giving you a bit of a warning to make sure that you are careful about what you're typing in and how you interpret those solutions. Okay, just moving along, so 2 more that I just wanted to look at, menu and calculus. And then you'll notice down the bottom here that we have tangent line. So if I push number 9 or tangent line, now the syntax for this, again, you could go through into your catalogue and find, but I'm just going to put in x squared. So we're going to find the equation of the tangent to the curve of x squared. Now we only need to tell the calculator what the x coordinate is, so at x equals 1. If we press enter, you'll actually find that the equation of the tangent to the curve y equals x squared at x equals 1 is y equals 2x take 1. Now, I'll be doing a little bit more with this later within one of the activities, so you'll sort of see a little bit more of how that can work. One thing I will recommend very strongly, having marked a lot of exams over the years, one of the issues here is don't just write down 2x take 1. Sometimes what we get from the calculator, we need to make sure that we put into mathematics. So the syntax on the calculator might be a little bit different to what the normal syntax mathematically might be. So please make sure that you put y equals 2x take 1, not just 2x take 1. Okay, and the last of our options is, again, in calculus, and down the bottom here at A is normal line. Now, for people who generally there's occasionally a couple of questions in exercises about normal lines as part of the applications of differentiation. A normal line, as people will be aware, where you have the gradient being perpendicular. So obviously we're looking at the multiple of or the reciprocal of our tangent equation. We're looking at the reciprocal of that and then with the negative inside in front of it. So if we do x squared, comma, x equals 1, same function, but now the normal to the curve rather than the tangent. And you'll notice that particularly the gradient part here, before it was 2 for the tangent, it's now negative 1 over 2 for the normal. So in other words, again, we've found the reciprocal of the original gradient and just put a negative sign in front of it. That's some very handy stuff because, again, often within the exams, they will actually ask you to find tangent lines. in a moment I'll show you some ways that you can pad it up in case you need to have some working out to be shown with it rather than just showing the answer. There are ways of actually setting the calculator up to make it so you can see a little bit of the working, which leads me into my second activity. So if we now move on to the one thing I was going to mention. Last week, Hayley, in her wonderful presentation that she did, mentioned some of the options in the algebra button under menu. So under number 3, I'm not going to go through all these again because I know Hayley touched on some of them, but there are some really handy things there in terms of expanding, things like factorising, your solve button, which would be one that you'd be very familiar with. Make sure that you have got some knowledge of those. I'm going to talk about zeros in a moment to make sure that people are familiar about what that does for you. But again, just get a little bit familiar with some of those options. The convert expression one I'll also try to have a look at before the end of this session. Okay, moving on. So looking at, I'll just escape out of that, sorry. So the next PowerPoint slide I want to have a look at is a bit of an exam question. So graphing functions using calculus, but including stationary points and pretty much the general things that you would be asked within an exam. Now, sometimes these might be a non-calculator question type problem, but they can also come up in the calculator section. So you may wish to obviously know these steps pretty well yourself without the calculator, but if you get lucky and you actually have one in the exam where it is in the calc section, then it would be really handy if you actually had something set up on your calculator to be able to just generate things straight away. The way we're going to do that is we're actually going to set up a notes page. So I'm going to go into the main menu, so into the home page. I'm going to set up a new document. I'm going to go no to saving the unsaved document because that was the things we were just working on. And I'm going to go into this feature called an add notes page, number 6. Now, a notes page can be just used for typing in, hi, my name is, and you can just put in normal notes, but it can be made very interactive as well. And that's the thing I want to spend probably the next 5 to 10 minutes on, just showing you how you can set up a really nice notes page that could actually work us through an exam question like the one that we've got on the left. So the first thing I'm going to do is I'm going to type in the word function, and if you've got your calculator there, you're welcome to try this out yourself. And at the end, it will be available on the Google downloads. But again, if you can actually have this set up for yourself as well. So I'm going to actually put in function. Then I'm going to just press enter to move down to the next line. Now, the next thing I want to do is I actually want to be able to enter in some function. Now, in this case, the function that we're defining is x cubed take 3x squared take 10x plus 24. So to set up a maths box, we're going to push Control and then M for math box, and you'll get this nice little broken line box that we can actually enter things into. Now I'm going to define that function as f of x. Now again, before we use the idea of control and then the colon equals, and then I'm going to type in the function that we've got here. So x cubed take 3x squared take 10x, sorry, I'm a bit slow in my typing tonight because I've got a telephone in one hand. It's a little bit of a balancing act here. Okay, so x cubed, take 3x squared, take 10x plus 24. Now, if we press return, you'll get done, and it'll actually now save that as a function. Now, I'll show you how that's really handy in a moment. Now, for the moment, that's really just us setting up a defined function. I'm now going to enter down a couple of spots just to give myself a little bit of structure. Now, the first thing that the question's asking us is to find the first derivative of that information. So I want to prompt myself, if I'm in an exam, to know what all this is meaning. So you notice I've actually come outside my maths box by just clicking outside of it. I'm going to put f of x as just normal text. Now, again, this is a very rushed one. I would put a lot more effort into presentation if I was doing this for a proper exam situation, although you don't want to be spending too much time wading through a whole lot of information. You want to be able to see answers nice and quickly on the screen. So we're going to have a look at f dash of x. Now, I'm going to use g of x as representing my first derivative. I'm going to, again, use the control and the colon equals to define. Now, as I said before, to get a shortcut for our derivative, it's shift and then the minus sign, which will bring the derivative template up. Put x, and then what do we want to do? We want to find the derivative of the function that we defined before, which is f of x. So now we have g of x being our first derivative, and we're finding the derivative of the original function. Now, if I press enter, it'll say done, which is not particularly exciting, but all that's now saying is, yes, it knows that that's a command. There are ways of hiding some of that stuff, but again, for tonight, I'll just focus on getting the main structure right. So we've got g of x in a maths box. If I now press enter, and again, you'll notice this is in bold, so it shows that, yes, it's recognising it as a function. If I press enter, now you'll notice up the top here, if it was x cubed, take 3x squared, take 10x plus 24. Yes, that seems to be differentiating it nicely. So straight away, we're actually getting the derivative function. Now later in the session, I'll show you that if you change this, it'll actually change what's going down the bottom here. I might just change one of the values by clicking in the box just to show you that there's a nice little cool trick that will happen here. So I'm just changing that to x to the power of 4. And if you watch the g of x box down lower, automatically it's changed it to being the new function and differentiating it correctly. I'll just change that back to the power of 3 so it doesn't affect what I'm doing for the rest of this. Okay, I'm going to go on the outside of our maths box again and just press enter a couple of times. The next thing that we may want to have later on is, I'm taking a guess, and I will tell you that if I come back into my PowerPoint, later it's going to talk about graphing the second derivative. It also talks about the nature of our points. So again, the second derivative could be a very useful thing for us to have. So I'm now going to come back into my emulator and put in f double dash of x, which again, you notice I'm typing outside the maths box. That way we can actually have it so it's just giving me a hint of this is what it's working out. Now I'm going to put in a new maths box, Control M, put h as being now my next letter in the alphabet, so that'll be my second derivative, is defined by, and now we want to find the derivative of our first differentiation. So I'm going to do d dx of g of x, so that way we're differentiating our first derivative. If I do that, it's done. Now I'll come down into the maths box and just type h of x to just get our answer generated. And if I do that, you'll notice now that we have our second derivative. Again, you can see up above, 3x squared take 6x take 10. Yes, the second derivative would be 6x take 6. Okay, I'd suggest that you don't try to put too much more on that page. I think that's now enough. And again, I'd be suggesting new pages for new tasks. That way that you're not getting too much clutter. One thing, again, you want in the exam is to be able to see things nice and quickly. So the next one, I'm going to insert Control I. So what we're going to do here is insert a new page, but still link to that problem. And again, I want another notes page, number 6. Now, the next thing that the question says is we want to find our stationary points. So stationary points. Now, as I said, this will be the 1 week that I actually go through and construct it like this. For the future, I'll have things a bit pre-prepared. But again, I think it's a valuable experience at this stage to actually see how one of these can be set up page by page. So what I want to do now is I want to find the stationary points. So I want the first derivative to be equal to 0. So I'm going to set up a maths page, a maths box, sorry, and I'm going to call it Z for zeros. So I'm going to make it equal to 0, my first derivative. I'm going to go Control and define it. Now, you could use solve and you could put it equal to 0, and what it'll do is it'll actually list things as x equals, x equals, x equals. Once you start getting functions that might have multiple values for when the derivative is equal to 0, it can get a little bit messy to read. It can get quite cumbersome to actually work through. So another option, and you can get this from the menus option, so if we go into menus and calculate, and you'll actually find that one of the options under algebra is number 4 zeros. So we can actually put that in. We want to put the first derivative equal to 0. So we're going to type in g of x, which was our first derivative. We're solving it for when it's x is our value that we're solving for. Press enter, it'll say done. Now what we'd want to do is just have a list of that. So z of x, you'll notice now it's recognising it as a function. Press enter, and you actually get 2 exact values because currently I'm set up as exact values in my, my setup for my document. If I decide I actually want that to be a decimal, you can actually move into that box, see how I'm now highlighting it, Control Enter, and it'll automatically change it into decimals for you without having to change your setup. If I press enter, it'll go back to being an exact value. I'd probably suggest leaving it in an exact value or auto, and that way if you need to change it to a decimal and have it to a certain amount of decimal places, it's already available and you can just do it quickly that way rather than trying to fiddle around with your settings. Okay, if we're doing stationary points, that now would be your X values. What we now want is the Y coordinate. So again, I believe in just prompting myself through these kind of problems. So Y coordinate, what do we want to do? We want the function with the X values, which are our zeros that we just got, being substituted into the original function. If I do that, you'll now find that we have two corresponding Y values that match up with our Z values, our X values. So there's the first X matches up with our Y, X and Y. So again, now we've actually got that set up. What would be the next thing? Well, it says identify the nature of these points. So moving on to part C, I'm going outside the math box. Again, I want to type in something to let me know what I'm actually doing. So it would be nature. I might want to prompt myself and say, well, if it's concave up, then the second derivative is going to be positive. If it's concave down, then the second derivative is going to be negative. And again, I'm just using abbreviations here to fit things in nicely on the screen. So what would we want to do there? We would want to have a maths box. So Control M. Put in H for our second derivative, and then we're going to substitute the zeros into that. If I press enter, you notice we'll get a negative value, so that would be a concave down situation or a maximum, and then concave up for positive. And again, these are all matching up. So if you read down the page, the X matches with the Y, which matches up with the concavity. Again, really easy to read. And if we change anything back here on the first page, so particularly if we change the original function, that will then play on to the next pages as well. So everything will change all the way through the pages. Okay, moving on. I would like to now look at the next part of this, which would probably be find the coordinates of the X and Y intercepts. So that's part D. So again, we're going to insert a new page, a new notes page, X int, and how do we do that? We make Y equals 0. So what we need to do is find the zeros this time. So I'm going to make a maths box, Control M, menu, calculations, and algebra, so 6 and 3, and number 4 for zeros. What are we trying to solve for zeros? Well, we're trying to find the X-intercept, so we're just going to make it function of X, and we're solving for X, and the zeros function means it's going to put that equal to 0. If I do that, there are my 3 X-intercepts when Y equals 0. Moving outside the box again, I'm going to make it Y-int. Again, prompting myself, because if we're asked to show working out, sometimes the question will show full calculus. Well, the way we're structuring this is actually giving you the lead-ins, the bit of information that you would use as part of your working out. So you can actually structure this so it is showing calculus, and you can just use this information to answer your question. So Y-intercept, we just want the function to have 0 as the X value, and there's our Y-intercept straight away. Really cool, and again, we can change anything that we need to as we go. Okay, what would be the next thing? We'd want to graph some of this information. So Control I, we're going to insert a graphs page. Now, there's a whole heap of ways, and tonight I'll probably just focus on one. The file that I'll be attaching, or has been attached to the Google Drive, will actually show you the way that you can actually split your screen up and maybe make it so that you have this information spread out on different graphs. But it's generally pretty useful to actually see all this information on the same set of axes. So in my graph page, the first one we had was f of x. Now, that's our first graph, not looking particularly useful at this stage, but if I go into Menu, Window Zoom, Zoom Fit often will give you a nice view of this, but we probably already have a bit of a view of what this graph is going to look like. It's not going to go much higher than what we need, so the min and max for the x values seem to be okay. It's more the y min and y max that seem to be a problem, so I might go down to about -30, I might go up to 30 and just see what that actually does in terms of our axes. Yeah, not too bad. Maybe could have gone a little bit higher for the y values, so maybe up to about 40. But again, we're starting to get a nice picture of the graph. If we now press Tab, and if we want to put in our second function, which is our first derivative, now being a cubic, we'd expect that to come out to be a quadratic if we've differentiated. And yep, very nicely we can actually see the overlap, particularly in colour, very clear what's going on. Okay, and then finally, we want our h of x, which is our second derivative. And again, that would not surprise us, I hope, because we've had a cubic, we've then got a quadratic, and then we've got a linear graph. So we've got a nice build-up of what's actually happening there. Okay, the final one, I won't probably go into the normal because I know we've got a whole lot of other things, but I'll just show you how, and again, this is all set up on the file that I'll be sending through to you. We might just quickly show you the tangent one. So, add notes. Now, again, we have got this function available in our menu, but the good thing about this is you can actually make it set up so that it shows you the steps, it shows you the working, so you actually look like you've got the right steps if it says using calculus or showing clear algebra. So I've just typed in there tangent and then enter the x value. So I'm going to go Control M for a maths box. I'm going to call my x value x1 just so it doesn't get confused with all the x's. Control and then define, and then I'm going to make that 2. So this is going to be the tangent when x equals 2. Just go outside that box. Again, I just want to prompt myself. So the tangent is going to be in the form of y equals mx plus c. And then we're going to have to work out the gradient. Okay, back into my maths box. So what we need to do here is find the gradient. I'm going to call that m of x, so a function of x, but using m, which we normally use for gradient. Colon equals. Now, what we need to do is obviously differentiate our original function. So shift, take an x, f of x. Then outside of this, I actually want to be telling it that derivative, if we push Control and equals, we can bring up the given sign. And then we're going to make it x is given by that x1 coordinate that we just typed in, so the x value. If I press Enter, I get done. Now again, like before, if I now just retype m of x, it's telling us what our gradient should be. So that's something that the exam might say, okay, you need to show the gradient. Now obviously then we need the y-intercept, is the other part of this, so outside the maths box. And we need to now come up with the c value that we'd normally have. So I'm going to call it c of x is given by. Now, you could do this on a piece of paper on the side, but basically the rearrangement is going to be the function with the x value substituted in. This is just a rearrangement. Take the gradient with the x1 typed in, or substituted in, and then times by the original x value. So that's just your rearrangement of your y equals mx plus c with the information we've already got. Let's get our y-intercept, which is 20. Then finally, the thing we'd want is the tangent. So again, I'm just going to go outside of all that. Tangent. So this is our final line. Now, we actually don't need to now get the calculator to do all this. I'm going to go out at the front of the box and just put y equals. I'm going to get the menu to do all the hard work for me now. Now I've got all the structure. I just want the final answer. So y equals, menu, calculation, number 4 for calculus, tangent line number 9. I'm going to type in f of x for the function. We want it to be doing it for x is equal to x1 using the syntax I used earlier, close bracket, and if I press enter, there's our tangent line. And you'll notice, yep, our y-intercept is 20, it's just been swapped around. Our y-intercept is 20, and our gradient is negative 10. So you've now got a page that can actually work it out, but also show you the steps as you go. Now, I was planning to do a normal with you, but I think I might skip over that. So I'll just show you the rest of this question. So it says find the equation of the tangent to the graph at x equals 2. Yep, we've done that. The normal, we could just set up a similar page, but do it for the normal, and then graph the function with the first derivative and second derivative, which we did back here in 1.4. Now remember, if you do want to go between pages, Control and then left or right will get you to the different pages that you might want set up. Okay. That will give, I might just have a break for a few minutes and catch my breath, and I know there's been a lot of information in there. I might pass back to Brian, who's now going to look at some trig function stuff with you and just show you some nice little cool tricks there. So passing back over to you, Brian.
Thanks, Stephen. And
yep.
Yeah, certainly. And that's just great stuff. That's real bread and butter stuff there, those styles of questions. And in fact, I was doing exactly that with my TAFE engineering students today, when we were looking at first derivative, second derivative, looking at points of intersection and turning points and points of inflection. All of that. It really helps when you've got the calculator there, which I tend to have put up on the screen for every lesson. Can I encourage students now? I understand that in your exam, of course, you've got the first component where you're not permitted to use these calculators. But I think there's just that the real power here is in using the screens and the technology to really assist your understanding. So to build up in seeing how all of those things relate to each other, and it really helps, I believe, in setting up that defined function fx, and then you can put in the values and equate it to 0 and so forth, and see those key points. And of course you also use it for the calculator active component of your exam. So Stephen's asked me to just review a little bit on trigonometric functions, some of the basic approaches to trig functions on your screens, and also the calculus of that, so and transformations of trig functions. So I'm hoping you see my screen now,
yep,
and you see
all good, Brian. Yep.
And again, I've got the PowerPoint next to the calculator. So the first one you got is given a function upon x equals sine x, solve for that equaling 0. Now, first thing to check, of course, is that your calculator is in Radian mode. It shouldn't really go out of that if you're just doing the methods course, because radians is what you work in. But if you've borrowed someone else's calculator or lent yours to someone else, then it may have inadvertently been switched into degrees. So just check on that. So what's going to happen, though, if I just ask this through the algebra menu to solve, that sine x, and I'll just use the keyboard here, sine x equaling 0 for values of x, what happens is I get this happening. So, what's this n1 pi bizzo? What this means is that it's giving me a general solution. So n is counting as an integer, and it could be positive, it could be negative, it could be 0. So basically it's saying x will equal multiples of pi. So the first one, the easiest one of that, is to substitute in for this n1, to substitute in 0. So x will equal 0 times pi, in other words, 0. And we know that from the graph of sine x, don't we? Let's just quickly look at the graph. So I'll put in a graph page. So sine x, and you can see that it equals 0, at 0, and it equals it again at pi, and it equals it again at 2 pi and 3 pi and so on. It will also equal 0 at negative pi, negative 2 pi. So it's counting by pi's. So that's a fairly straightforward one. But take a look at our question. It's actually asking us to only give the solutions across a specified domain, negative 2 pi, in other words, one circle to the left, and 2 pi, one circle to the right. So it'll be all up a 720-degree rotation. But what I can do is I'll just recall that command. But before executing it, I'll put the restricted domain. So by going second and then down on this key here on the equal sign, it brings up this suite of goodies. And this one here, this vertical line, that means given that, or providing the conditions. So given that negative 2 pi, and the pi key is under here, is less than or equal to x, which itself is less than or equal to 2 pi. Okay, and we'll go back under here. Another interesting one is that if you're just working off the keyboard, you can actually put in the letters pi. It will recognise the letters pi for pi. So here we have the specific values. So it's negative 2 pi, negative 1 pi, 0, and positive 1 pi and positive 2 pi. Okay, and some transformations here. I'm actually going to do some harder ones, Stephen. These are the ones that were assigned here. X plus pi, well, that will have the effect of moving our graph. There's our graph. That would have the effect of moving our graph pi units to the left. Or would it be pi to the right? It might be difficult to actually tell, so I'm going to skip that one. Fx equals 2x, in other words, 2 times the sine of x. So what that will do is it will make it twice as frequent. And what if I doubled the function? It'll make it twice as high or increase the amplitude. So I've chosen a more complicated one to look at, and this is it here. So I've got my function is, I'm going with cosine, and I'm going with 4 times the cosine of all of 2 times all of x minus pi on 6 plus 5 for good luck. Wow, that's going to be a mess. But let's do it in bit by bit just to show how all those transformations work. So I will tab up here, and so instead of the function being sine x, let's make it cosine x. And okay, so now I'm starting at 1 rather than starting at 0. That's cool. So I've done part A here. What would happen if I made it the cosine of not x, but x minus, and I'm going to use that shortcut I told you about. I'm going to put in pi because I'm just working off one-handed on the keyboard while I hold the phone with the other. Pi on 6. So the cosine of x minus pi on 6, what it's done is it's moved our graph. You can see the original blue. It's the red is the new one. It's moved at pi on 6 units across to the right. So remember, minus pi on 6 actually moves it to the right. If it was a positive pi on 6, it would translate to the left. So part C we're now up to. What if I doubled all of that? So I'm going to go up here. I will tab up, and instead of having cos x minus pi on 6, I'm going to have cos, and I'll open up my brackets, 2 multiplied by, and I'll commence another bracket, x minus pi on 6, and I'll allow the calculator to close the brackets for me. And what's happened is it's made it twice as frequent. So that 2 has the effect of doubling the frequency or halving the period. Let's just go up. I'm going to cut the blue one out because we get too much on the screen. It just makes it look a little bit too confusing. So you can see the red one here, and there's a maximum there, and there's the next maximum. But in the time that the red curve has one period, the black one has gone down and up twice. So that's the effect of that 2. Now, our next part is, let's multiply the whole shebang by 4. So are you happy for me to just... Sorry, I'll go back into the tab. Are you happy for me to do that shortcut by saying, there's the previous one. If I want to multiply the whole shebang by 4, this thing here is function 3 of x. Can I just make it my fourth function being 4 multiplied by function 3 of x? And you can see what that's done is it's just increased the amplitude, so blown it up. And once again, I'm going to also get rid of my earlier one here. I'll tick this one out now. So you can see the black one, which was our previous one, and the mauvey one, which is now 4 times the amplitude. Now, the last step here was to add 5 at the end. And of course, if you do this to any graph, any function, So I'm now going to say my fifth function is, well, shall I, rather than type everything in again, it equals the fourth function of x, which you saw just set up, and I'm going to add 5. And that has the effect of just pushing everything up. Once again, I'm going to get rid of the earlier one. So we'll take out our F3 this time. So you only see F4 and F5. And F5 is just like F4, pushed up 5 units. Okay, so that's our transpositions there. But we haven't got any calculus in that. But no, I'm going to skip this here. You could know how to do this. I could now solve this for the general solution, and I could solve it. If I put it equal to 7, look, I will just for the fun of it. Why not? I'll come onto the calculator. Let's get rid of the mauve graph. So we'll only deal with our final function, which you see there graphed in green. And I'm also going to graph function on x equals 7. Okay, so I want to know where those two lines intersect, or where those two curves intersect. Where does the green cosine curve intersect the orange line 7? And you can see it intersects there. It's an infinite number of solutions. So if I actually did solve, and I've got it over here, so if I said solve all of this equals 7 for x, and I think that should work. I'm going to get, there's the general solution, and I can start this by plugging in the simplest one is to substitute in 0 for this. That's the easiest integer. So x will equal 0 times pi. Guess what? That's going to look very much like 0. And as you can see there, there it is. So when x equals 0, I've got a point of intersection. I could also do that by analysing the graph here, but using the analyse tool. But just on this, that's what's happened here. And you know the deal that I could also do it with the restricted domain to answer part B of the question here, using what I showed you earlier. Given that, what am I saying, 0 is less than or equal to x, is itself less than or equal to 2 pi. And so there's our specific 1, 2, 3, 4, 5 solutions across that domain, that restricted domain. And you see it's 1, 2, 3, 4, 5. There they are. We haven't got any calculus in that, but let's look at what's in your syllabus. I'm going to biggerise this so we can see it. In your syllabus document, biggerise it too much. Okay, so establishing the formulas that the derivative of sine is in fact cosine, and the derivative of cosine is, well, people then think, well, hey, let's go the other way, that'll be sine. No, it's not, it's negative sine. And the other one that isn't written there is that the derivative of tan equaling 1 divided by the square of cosine, or in other words, sec squared x. So how does that work? I think the easiest way to look at this is graphically, geometric construction. And I think to get the tan one, it actually is easiest going through the quotient rule. So I'll just quickly have a look at that. And then you're also asked to do such things as the product and quotient and chain rules, solving things such as differentiating x sine x, x multiplied by sine x, that is, and e to the negative x multiplied by sine x, and so forth. And this one here being a chain rule. So let's have a look at this. As I said, this one is best done graphically. Every time I teach it, I do it graphically, point by point. And I thought for tonight's webinar, I would find a really beautiful little Inspire file for this, and I did. I found a lovely one Now, guys, you saw Stephen just develop a wonderful file before your eyes, and that was pretty good. I tend to be fairly lazy. I tend to not write so many of these files because I know for a fact that Stephen is posting that file into the share folder for tonight's webinar, so you will get a copy. So by all means, it's lovely to be able to write them yourself, but cripes, if somebody else has written it for you, then why go to the trouble? I just Googled, can I please have a TNS file of a derivative, a graph and its derivative, and I found it. And it was written by a fellow by the name of Jody Crothers, who teaches in Western Australia. And he is actually teaching the applications course for this webinar series. So there you go. I just typed Google, looking for a solution, and where are the experts? Here in our very own program. And I also know that Jody is online tonight. So thanks, Jody. That's very nice. You wrote this a couple of years ago. And this works by putting in a function using the dynamic notes pages, which Stephen and Jody have already, and Hayley have already shown you. Type in a function here. So the function is on x is sine x. It's done. And then on the next page, here's the sine x function. And I can grab this red point, which is the tangent line, which of course is the derivative. The gradient of the tangent line is the derivative. And look at this. As I move this through, so you can see here, for example, the tangent is 1. The slope of that black line is 1. And so up here on the mauve graph, you see 1 being plotted. If I move the red line, the red dot further, you can see the slope is decreasing. The slope of that black line is going down. And it's going down and going down. It's still positive, but it's going down. And when I get to the turning point, one of those critical points that Stephen was just showing you, so that's the maximum here, the gradient, the slope, the steepness, whatever you want to call it, of that black line is now 0. And look what's happened on the mauve graph. It's gone down to 0. If I move my red dot further, then the gradient is now negative. Okay, so the mauve graph has gone below the x-axis. In other words, it's negative. And it keeps getting steeper and steeper, more and more negative, and more negative. And you see, I get here, it's actually -1 at that point, -1. And if I continue on, it's still negative, but it's not as much negative. So you can see that it's still in the negative area here, but it's not as much negative until I get right to this next turning point where it is 0. And if you look at this mauve graph that we've just produced, that will look very much like the familiar cosine graph. So the blue graph is sine x. The mauve graph is its derivative, which is cosine x. And I can go back here, I'm sorry, it says over here, therefore the derivative of sine x equals cosine x. I can go back here and change this to cosine x. So it's done, and I can look at this, and you see the blue one here is the cosine x, and its derivative is not sine x, but it's the negative of sine x. Can you see that? Because if I actually graphed sine x on here, it's up here. So you can see that the mauve, which is the derivative of the blue, is the negative of sine x, and so on. And that's just a lovely little program. I can put all sorts of things in here, and I see its derivatives. I could put in the one that that Stephen was demonstrating to you, but I'm running short of time. I had to finish up an exam type question, and of course the exam type questions they're always rather silly, aren't they? We have this absolutely bizarre story and bizarre names. So, for example, in the city of Trigonometric Trigonometric. Yes, that's a little bit made up. The people engineered a special ornamental river modelled by the function y equals 4 times the cosine. This is the function that we graphed earlier. Why on earth people would want a river like that, I don't really know, but they occur in the stories of maths exam questions. Now, X is indicating how far east of the city centre. So here's a graph. Imagine this is the city centre here. So as we move to the right, as you would normally on a map, that's to the east of the city centre. And as we move up the page, we're moving to the north. The story goes on to tell us that at the point 1, 2, there is the post office, and at the point 3, 5, there is the town hall. And for some reason they wanted to build a direct road, straight line road between these two places, building bridges over the river as required. What is the length of the road? Well, that's just the distance between 2 points. So distance between 2 points formula. How much of the road will be north of the river? Stephen, I'm going to cut short of running right through this, but I did do it here. This is the picture. I put the points in, the point 1, 2. So this is our post office, that point there, and the point 3, 5. I'll get this out of the way. There's the point 3, 5 over here, and then I graphed it, put a line between them, found the equation of that line. Here it is. It's y equals 1.5x plus 0.5, and I intersected that line with the river. Got the 2 point intersection. That's one of them. That's the one there, and this is the one over here. And then I quite cleverly used that distance between 2 points in a notes page to get the distance between them. So that's just the sort of stuff you can have set up in advance if you've got this sort of notes pages. Stephen, I've gone over time, so I'm just going to hand back to you because I know there's a wealth of stuff to look at, but we're going over our time.
Yeah, look, I probably, I was going to say, Brian, I did have a few other things I would like to have looked at. I don't know if you've, probably might be, you've put it over to me. That's all right.
Back to you.
I probably won't do too much more because I know we're getting close to the 6 o'clock. You should see my screen back up again, I think. So come back up, Brian? Yep. Now I might even start a couple of these little quick activities for our next session next week, even though I know it's all about integration and anti-differentiation. I guess the only last thing I wanted to quickly touch on, and then I'll pass back to you, is obviously with these notes pages, if you are creating your own or if you're getting them off the internet like Brian's just showing you a couple of really, really cool ones there, obviously you can save them. So Hayley went through that, and if you want to look at last week's webinar, it was just Control-S. I won't actually do it here for time reasons now, but Control-S, and you actually have a chance to save these files and put them into your doc area. And again, they can be brought up by my doc back on your home page. I guess the last thing I just wanted to quickly touch on with my one was I talked about being able to change things. You may notice number 5 on my exam questions here, showing the clear use of calculus, sketch the graph of x squared e to the x. I noticed that was actually one of them on the syllabus document that Brian was just showing you. If I just come in here and put x squared, and I just want to show you that this can handle pretty complex rules actually. And the other quick one I wanted to touch on is be careful about which E you use in terms of exponentials. I had a student a few years ago who went through a whole exam, and even though he'd been warned by me, decided to use the letter E rather than the exponential E. So again, make sure you are using the function. That's a very big common mistake that students make, is that they use the letter E and it just becomes a constant rather than using the variable idea. If I just press enter now, and what you'll notice is even though it's a fairly complex rule, all down the bottom here you'll start seeing that things have been changed to the appropriate rule. I again won't go through all the pages, but again you'll see that everything's now in terms of E, so you can appreciate that this has actually worked out things for the more complex function. The graphs are getting a little bit more harder to see, so you'd have to enlarge that. But again, even to the tangent lines, it's giving us things based on that first change. So everything has been changed based on that very, very, very first screen. So, look, on that note, Brian, I think rather than trying to rush through too much else, there's a couple of little other shortcuts, but I can start that with them off at the first part of our next session next Monday. So, I think I'll pass back over to you. I think we've got through a lot of information tonight anyway.
Thanks, Stephen. We certainly have. And can I just remind students that they will be receiving an email as a follow-up that takes them to, which has a link in that, taking them to a page of a Google Drive where we have shared the notes. So this PowerPoint will be part of it. So the pages that we've got there with the notes on natural logarithms and e to the x. And so that is shared along with a couple of those Inspire files. And if you want to have a go at it, these are the further questions that we didn't get up to. So some practice exam questions there.
And I'll just say Brian, one of the other files that have been included is one to do with rectilinear motion as well. Again, I might very briefly touch on that on our next Monday session, just to show people how it can be used. But yeah, thanks for that.
Fantastic. As always, the time flies when we're having fun. So well done, participants. We appreciate that you're very busy, and you'll be busy studying for many hours further into the night, won't you? Look out for the email with the links there to all those wonderful files, and we will look forward to seeing you again next week. Thanks to Stephen. Cheers.
Thank you, Brian. Thank you, everyone. Good night.